Okay, so we are doing chapter 3.4. We're going to do logs and exponents today. We're actually going to start with the exponents, and that's what we're going to deal with today, is solving exponential equations. So this one kind of harks back to the first day we started dealing with logs and the switching and finding that if I change the base of some exponents, they don't change the actual value, but the look of it. And so we're going to use that to our advantage here. And the whole idea is that if I say two numbers are equal, I want those two numbers to have the same base, because to be equal with the same base, that means their exponents have to be the same. So this is all about trying to change the look of something without changing its value. 4 quarters for $1 is okay. 2 squared instead of 4 is okay. 3 to the third is okay for 27, because those are equivalent pieces. So our goal is to somehow make it so 16 and 4 have the same base. What number, when I have a power on it, can be 16 and 4? There happens to be 2 options. 2, because 2 to what power is 16? 4. 2 to the 4th power is 16. And 2 to what power is 4? 2. That would allow me to actually replace 16 and 4 with base 2. Is there another option that might actually be easier for us? I don't have to do both. Just a 4. Because 4 to the first power is 4. I got this taken care of. But then I come over here and say, hey, wait a minute. 16 is 4 squared. So I'm going to replace 16 with 4 squared. Do not mess with x plus 3. It's still an exponent on 16, aka 4 squared. So this is 4x plus 7. Now, if kids or students are going to make some mistakes, this is the point where they make it. They don't realize that you can get a common base, number 1. But number 2, once they do that, they forget that this 2 is multiplied to a binomial, sometimes a trinomial. You need to make sure that you distribute the 2. And so 2 times x is, and 2 times 3, 6. And now we have it that 2 numbers are equal, and so are their bases. So the only way for these 2 numbers to be equal is if the exponents are the same. It's the only way. And so, when does 2x plus 6 equal 4x plus 7? Now we just created an Algebra 1 problem. And again, for most of us, the hard part is going to be trying to set it up so that we have that common base. Because it's not always going to be straightforward. Some of the numbers are going to get a little bit larger, so you're going to have to kind of work your way through some of your numbers. This is where it's kind of nice to know your perfect squares, perfect cubes, and all of those. Now solve it. Subtract 2x, yeah? Subtract 7 while we're at it. So negative 1 equals 2x. And then divide both sides by 2. So x equals negative 1/2. Now, the good student would go back, make sure that if I put negative 1/2 into both of these, I'll end up getting the same answer. Remember, when checking, you can't cross the road. The equal sign, you can't cross it. It's a wall there. And so the left-hand side should equal the right-hand side. If we do these things correctly, these should work. It's when we start to get to the point where you're going to have squares and quadratics and cubics and your square rooting and all of that, then you really have to start watching for those extraneous solutions. But we don't have to worry about those right at this point. Does that make sense, guys? Get a common base. Every problem in your worksheet has a common base. Don't say there is none. Work at it. Because now you get things like this. 2/3 to the x minus 5 equals 9/4 to the 3x over 4. So now it's a fractional base. And now remember, when we say base, it's a base with an exponent. And how do we take exponents of fractions? If I square a fraction, I square the top and the bottom, the numerator, denominator. If I cube a fraction, I cube the top and I cube the bottom. So be very mindful of that. Also, you're looking at this problem going, okay, 2/3. Can that somehow be broken down even more? I don't think so. I think 2/3 is about as small of a integers or factors as I can go, right? But 9 and 4. 9 is actually a perfect, and 4 is a perfect square. It's a perfect square of 3/2. So definitely I like the 3 and the 2. I'm not going to change this guy. But I want to get 2/3 over here then. Now, how did I go from a 2 to a 4, a 3 to a 9?
How did you do that?
No, just hold on. Hold on. Guys, I have to have these be the same, yes?
Yeah.
Okay.
You said 2 to a 4.
Now,
3 to a 9.
yeah, I know.
That's out.
That it would be this different thinking. Watch, listen to this magic here. Okay. Somehow, I went from what you guys said, hey, wait, that's opposite. The 9 or the 3 should have been on top, and the 2 should have been on the bottom, right?
Yeah.
And I went the other way and split 2 here, 3 here, because I needed to match. They need to match up. Well, wait a minute. What number in exponents takes things from the top, moves it to the bottom, and the bottom to the top?
Negative.
That's a negative. So negative exponent, guys, that means 2/3 is definitely going to have a negative exponent. Now, I have now flipped it. Now it's right side up, as we'll say.
I really don't like that.
And so now, you can still think to yourself, 2 becomes a 4, a 3 becomes a 9, because I did what to them? Square them. So if I take 2/3 to the negative 2 power, I'm squaring it and flipping it, which results in 9/4. Awesome. But here's the thing. All of that stuff on the right-hand side here just stands for 9/4. So I need a bigger set of parentheses. And outside that bigger set of parentheses, I have to put 9x/4. Did I say 9x? I meant 3x/4. Just seeing if anybody's listening. And I have power of a power again, and so therefore you multiply. Now, okay, that's 2/3 to the x minus 5 equals 2/3 to the, wait a minute, I have a 2 on top, I have a 4 on the bottom. Couldn't I just simplify that right away? Would you guys be okay with saying, I can get rid of the 2 and the 4 and make that a 2?
No.
Because one's on top, one's on the bottom.
No, I don't like that.
And so it becomes negative 3x/2.
This is crazy. Are you recording this?
Yes, I am.
Good.
Now, the bases are the same, the numbers are the same, so therefore the exponents are the same. So, when does x minus 5 equal a negative 3x/2?
What's that?
Okay, so I'm hearing add 5 to both sides, which is a very logical thing to do.
Thank you. I am logical.
That's fine, right?
Multiple by 2.
But I think I like what I also hear. Multiply by 2.
Yeah.
Because guess what? There is a fraction. And so 2 is the only denominator, aka the LCD. I can fraction bust by multiplying both sides of the fraction by 2. And so, I multiply 2 and 2, whoops, because those cancel each other out. 2x minus 10 equals negative 6x. Oh, sorry. Negative 3x, my bad. Okay, we have options. You could add 3x or subtract 2x.
Subtract 2x.
Okay. No, we're doing left side, right side. That is true if you don't change a fraction. But what you do to the left side of the equal sign, you do to the right.
Then you get
That's crazy.
So negative 10 equals negative 5x. Divide both sides.
X equals 2.
X equals 2. And again, check it. It'll work.
Wait, would you have gotten the same thing if you did?
Homework is worksheet number 12, which is something about why is the Papa Shoe mad at its son. Have a great day.